Sometimes the block is on a flat surface. Sometimes a block is on a slanted surface. Sometimes it's on a really slanted surface. And if it's so slanted that it's straight up, then the block could just fall. Now, in a situation like, for each of these situations, we'll call this A, B, C, and D. There are no forces on the block besides its weight and the normal force from the surface. So in situation A, will the block move? No. With no external forces, the block is not going to move because the normal force is pointing up, the weight is pointing down, they exactly counteract each other. In situation D, will the block move? Yes, the block will move, it will fall straight down because there's nothing to stop it. Now in situation B or C, how do we know if the block will move or not? How do we know how slanted the surface has to be to make the block move? That's what we're going to look at in this example. So let's say there's a block on a plane, and the plane is at some angle theta. So here is the block, here is the plane. So how do we know what angle is going to cause this block to slide? Or what other factors even matter? So if there's friction on here, then the block might not slide. If there's no friction, of course it's going to fall because there's nothing pushing against it. But if there is friction, then how much friction is enough to keep the block from moving? Well, we draw the forces on it. Then we know that the weight points down, the normal force points into the plane, and the friction force points up on the plane to keep that block from moving. So then if we assign a coordinate frame, say X points down, Y points up, and then at the exact instant when the block starts to move, the friction is going to be its maximum. So let's say if we write out the forces, we'll have in the Y direction, sum of the forces in Y equals normal force points up, and then gravity points down. But so if this angle of the plane right here is theta, then that means this angle right here between the normal force and the gravity is also theta. So then it's the cosine component that points into the plane. So n minus mg cosine theta in the Y direction, and then the block does not move off of the plane, so we know that equals 0. N equals mg cos theta. You need to be able to get pretty good at figuring out whether it's cosine or sine that points into the plane versus down. Generally, in a situation like this, the cosine points into the plane and the sine points along it. That's helpful to remember, but you can always draw out the diagram if you forget. Now, we know that the friction force, F equals mu times the normal force, which equals mu mg cosine theta. So in the x direction, we need to check, is the weight of the block, the part of the block that's pulling down the plane, is that enough to overcome the friction? Like, what is the minimum that you need? So sum of the forces in the x direction, since we want the absolute minimum angle to make this, and friction to make this block like slide versus stay, we'll say that's 0. 0 is going to be at very minimum acceleration. So what points down? Well, we have a component of the weight. It'll be the sine component because it's this part right here. It's the sine of that angle. mg sine theta. And then the friction force points back up. Minus mu mg cosine theta. Well, conveniently here, we can see there's a lot of stuff that'll cancel. So if we move this to the other side, mu mg cos theta equals mg sine theta, we can see here, mass cancels. So that's interesting. It doesn't depend on the mass of the block. The mass of the block does not affect whether or not the block is actually going to slide. And then gravity also cancels. Acceleration due to gravity doesn't matter. It doesn't matter what planet you're on. So then what we're left with here, mu equals sine theta over cosine theta equals tangent theta. So the friction to keep this block from sliding has to be greater than the tangent of theta. If the block does slide, that means tangent theta is greater than the friction coefficient. So the angle that the block will slide at is going to be tan inverse of the coefficient equals theta. So this is absolutely fascinating, that whether or not a block will slide on a plane does not depend on the mass of the block. It does not depend on the acceleration due to gravity. It only depends on friction of the surface and the angle of the plane. So at some certain angle, it's going to be enough that the block will overcome that friction and just slide down. Now we can actually test this out. Set up an experiment. I have 2 books here. There's the big book on top, the small book on the bottom. They're both pretty equally sized area, but they're different masses. So first, we're going to weigh it and make sure that they are different masses. All right, so we're going to weigh the first book. This one is 971 grams. Now we're going to weigh the second book. This one is 1336 grams. So we know the second book is about 50% heavier than the first book. So I'm going to set both of these books on here, and we'll put them on paper to make sure that coefficients of friction are exactly the same. So first book, second book. Then I'm going to lift up the table and we're going to see if they slide at the same time. So if the friction is only dependent on the angle, not dependent on the mass, then they should start sliding at the same time. All right, so now I'm going to slowly lift this up and we should see that the blocks slide at the same time. So there was a little slight variation there, which may have been like shaking the table wrong or something, but you can see they basically slid at the same angle of table. So just because one was 50% heavier, it didn't make the angle need to be 50% higher. So we can see that the angle and the coefficient of friction are not dependent on the masses of the two objects.